Hello everyone. Under structure and bonding topic, I'm going to discuss about energetics of hybridization, Bend's rule and resonance. Energetics of hybridization. We know that when orbitals are intermixed and forms the hybrid orbitals. The formation of hybrid orbitals, they loses the energy. When it overlap with any atom of orbital, they forms the sigma bond. That means the formation of bond is a exothermic process. In energetics of hybridization, it is the difference between the orbitals while undergoing hybridization of energy, or it is a energy released after hybridization has takes place. In hybridization process, the s orbital energy will slightly increases and p orbital energy will slightly decreases, but hybrid orbitals are having intermediate energy. This determines the shape or structure of the molecules and especially based on the contribution of s and p orbital. Let's explain this with one example. In methane molecule, we know that it is sp3 hybridized. It contains 2s2, 2p2 electron in its valence orbital. When electron in 2s is excited or promoted, one electron is shifted to the 2p orbital, and 2s and 2p orbital having unpaired electron, and these two orbitals show the interaction between them. When they are interacted, they undergo hybridization process and forms hybrid orbitals of sp3 having unpaired electrons in each orbital with same energy. Here there is no change in energy of the orbital. But in the case of ammonia molecule, the lone pair of electron is present in 2s orbital, and in p orbital unpaired electron is present. It is easily available for overlapping with hydrogen atoms, and this 2s orbital is promoted to the sp3 hybrid state by change in energy. This requires some excitation energy, and it responsible for change in geometry of the molecule from tetrahedral to the pyramidal. And to overcome this type of problem, in 1961, Henry Bent explained the relationship between the orbital hybridization of central atom and electronegativity of substance. According to the Bent rule, it states that atomic s character tend to concentrate in orbital that are directed toward electropositive group, and atomic p character tend to concentrate in orbital that are directed towards electronegative group. Or we can say like this: more electronegative substituent prefer hybrid orbitals
having less s character,
and more electropositive substituent prefer hybrid orbital having more s character. We can say like this: a central atom which having both s and p character. The central atom, it sends its character to the electropositive substituent. The p character will prefer for electronegative substituent. The S character is directly proportional to the bond angle, but it is inversely proportional to the bond length. P character is directly proportional to the bond length. The bond energy becomes very less, or it is decreases. More P character, bond length will be more, but bond energy will decreases. In case of S character, if the S character is more, the bond angle is increases and the bond length is decreases. The S orbital has lower energy than P orbital. S orbital are more penetrating and electron density is less available for bonding. Thus, more electronegative atoms would be able to withdraw more electron density from P orbitals than S orbital, because the S orbitals are present very nearer to the nucleus. Electron density is less available for donation. By all this, we can say that a lone pair of electron and multiple bonds are preferred to occupy the equatorial position, means which having greater S percentage character, and a more electronegative atom or group prefer to occupy the axial position where percentage of S character is very less. This can be explained with example of trigonal bipyramidal sp3d hybridized in PCl3F2. We know that it is trigonal bipyramidal geometry. Phosphorus is the central atom. Preference of chlorine and fluorine are placed according to the Bend's rule. Here, the fluorine is more electronegative than the chlorine. Therefore, it will occupy the axial position, and the chlorine occupy the equatorial position. The bond angle is here 120 degree and here 90 degree. The fluorine is more electronegative than chlorine. Therefore, the P character is increases here and S character is decreases. And the another example, that is CH2F2. It is sp3 hybridized tetrahedral structure for CH2F2. In this, the bond angle between the FCF is very less than compared to the bond angle between HCH, and this can also be explained based on Bend's rule. Here, the fluorine is more electronegative than the hydrogen. Because of this, the P character is increases. As P character increases, this bond length will increases. We can give many example for sp3d hybridization. These are example, and the shape will become seesaw shape for SF4 and T shape for the ClF3. And the next one, limitation of Bend's rule. It is not applicable for transition metal.
In octahedral, all bond lengths are equal.
And also in pentagonal bipyramidal, the Bend rule is modified. The orbital having more space will have more S character. According to this modified Bend rule, the axial position is occupied by lone pair or multiple bond. The equatorial position occupied by more electronegative atom or group. For example, XeF5-. It is sp3d3 hybridized, having pentagonal bipyramidal geometry, but its shape will be pentagonal planar. Application: it helps to explain the bond angle, bond strength, bond length, and also helps in to explain the inductive effect in organic molecules. This is about Bend's rule and energetics of hybridization. Next concept, resonance. When a molecule or ion is represented by two or more structures that are different in position of electrons and not in position of atoms, then each of the structure is called resonating structure or canonical structure, and this phenomena is termed as resonance. Condition for resonance: in this, all participating atoms must be in same plane. The second one, resonating structure should have same position of an atom and should differ only in position of electron. For example, these two are the resonating structure of benzene, and this is the resonance hybrid. Here, the pi bond position will be different, or the pi electron position will be different. Position of carbon atom will be same. We can calculate the bond order for this resonating structures. Bond order is equals to total number of bond divided by total number of resonating structure. In this structure, double bond is present and single bond is present, 2 plus 1, and the total number of resonating structure is 2, not 3, 2. So it gives 3 by 2 means 1.5. Next condition, the number of unpaired electrons should be same in all canonical form. For example, carbonate ion. In this, the number of unpaired electron in all structure would be the same. And bond order for this structure, total bond is 4 and resonating structures are 3. Therefore, we get 1.33. Next condition, resonating structure should have nearly same energy. Resonating structure should have negative charge on electronegative atom and positive charge on electropositive atom. For example, in HF molecule, the hydrogen having positive charge, fluorine having negative charge. According to this condition, the negative charge present on electronegative atom and positive charge present on electropositive atom. Resonance energy. Resonance energy means it is the energy difference between the most stable resonating structure and resonance hybrid. Resonance energy is expressed in terms of kilocalorie per mole or kilojoule per mole. Resonance energy is always negative. Energy diagram for benzene, and this is the resonance hybrid. The resonance hybrid having less energy and it is more stable compared to the most canonical structure of benzene. Energy difference between these two structure is a resonance energy. The resonance energy of benzene is minus 36 kilocalorie per mole. Resonance energy will more, the stability of the molecule will also increases. The resonance energy is calculated by heat in hydrogenation. Benzene is treated with hydrogen in presence of nickel. It forms cyclohexane. The change in energy we can calculate like this. Minus 29 multiplied by 3, we get minus 87 kilocalorie per mole. For one double bond to break, we require 29 kilocalorie per mole amount of energy. Here we are breaking 3 double bonds, therefore we get minus 87 kilocalorie per mole. But experimentally, minus 51 kilocalorie per mole. And the resonance energy for benzene is observed energy minus experimental energy. We get minus 36 kilocalorie per mole.